All right, so here we go. Okay, so dot product versus cross product in applications. So determining which one you would use just goes right back to what we just said. So the dot product would be for quantities that are optimized or maximized when what? When the contributing vectors are in the same direction, or 0 when orthogonal. So this just goes along with what we said. And then the cross product would be used in applications for quantities that are optimized or maximized when contributing vectors are orthogonal, or are 0 when parallel. So that should just go right along with what we said. Does that make sense? So for instance, we want to find the actual velocity of the boat. We have the trajectory of the boat and the current. And we want to find the actual velocity of the boat. Would that be dot product or cross product? Dot, right? It'd be like dot because it would have to do with your maximum. You would maximize their actual velocity when they were the same direction, right? And you'd be 0. There would be no. You wouldn't be contributing to each other when they're orthogonal. What about like a light shining on a solar panel? Would that be a matter of dot product or cross product? Cross product. You want the perpendicular, right? You're getting the maximum energy from a solar panel when the sun's shining right at it. Okay, what about torque? So this vector is called the radial vector. It's the vector, the tip is at the center of rotation. And sorry, the tail is at the center of rotation, like where the bolt is. And the tip is where you're applying the force. And then this vector is the force vector. So would torque be calculated by R dot F or R cross F? People are saying cross. Agree with that? That's right. So R cross F would be you only want this component of the force. And so this turns out to be, this is actually right here. This is the angle between the vectors tail to tail. That's why I moved this vector over here to show the angle between them tail to tail. And you see that that angle is the same as this angle. And this component of F would be a matter of sine theta or cosine theta? Sine, which is our, right? That's our cross product.
So the way you write it, you just put the magnitude bars on?
No, we're just talking about magnitude right now. So I'll talk about direction in a second. So just talking about the magnitude of the torque, how much twisting force would be the component of F perpendicular to R times R. And that's the magnitude of the cross product. Does that make sense?
Yeah. I'm just confused because dot product, you multiply R times F as well. You just...
Oh, I should have burnt sine. This is sine. If you're very uncomfortable, good. That should have been sine. Okay, that's right now. Sorry. It's cutter at you.
Well, my question was, so the dot product, you're multiplying R by F, right? And you're getting a scalar. But the cross product, you're still multiplying R by F. So how do you determine, like, when in your writing to show that you're doing cross product and not dot product?
The little x.
That's the X.
The x is, yeah, the dot is dot product and the x is cross product. Okay, so what about the direction then? So this would give this is amount of torque. So so this is showing two ways to calculate it. You could actually do the cross product like you did in the quiz, get the components and find the magnitude of that, or you could find the magnitudes of the individual vectors and multiply it by the sine of theta. It'll be the same answer, and it's both the amount of torque that you're putting on that bolt. Now what about the direction? So using the right-hand rule, will this, so use the right-hand rule, this practice, to figure out if the bolt will turn clockwise or counterclockwise. So use the right-hand rule and figure out, wait a sec. No, just not clockwise or counterclockwise, but what is the direction of the torque? Use the right-hand rule. Someone said something? Into the screen. Agree with that? So it's R cross F. I'm going to point my index finger in the direction of R and then my third finger in the direction of F.
So it's going to be out of the
You see it's out of the screen, Elena? So because I got my index finger in the direction of R, and then my third finger in the direction of F, that would have my thumb has to be out. What's that? It's not X and Y. X, the index finger is the first vector in the cross product, and the third finger is the second vector in the cross product. So it's not a matter of X, Y, or Z, because we could be twisted anywhere in X, Y, and Z. So the first vector R, index finger, second vector F, third finger. So what happens, right? So which way are we turning the bolt? Kyle.
Is there an algebraic way to figure out the direction of the vector? Because that right finger hand thing, whatever it is, not makes sense.
Yeah, if you just find the cross product, then you'll have the components, and that will determine the direction. Like if you have the components of the vector, then that has everything. Like you just got it. What's that?
I know. Yep.
That's just it could be any direction in three-dimensional space. And then if you had the components of the actual cross product, then you could draw it, and that would be the direction of the vector. But I would keep working on it, Kyle, don't give up. I would keep working on it. It's important to be able to just do that quick and do the use the right-hand rule. Yeah. Okay, so what direction is the bolt gonna turn? Clockwise or counterclockwise, according to F? Counterclockwise, right? We're actually pulling this way, right? We're turning counterclockwise. And then if you turn a bolt counterclockwise, which way does it go? Does it go in or out? Lefty-loosey, right? You know, it's left, righty-tighty, lefty-loosey. And so what do you notice? That's the direction of the cross product. See that? That was the cross product was coming out of the screen. Well, that's the way the bolt comes when you turn it. It comes out of the screen. So bolts are the standard threading is according to the right-hand rule. So that when you twist it counterclockwise, it comes out according to the right-hand rule. Make sense? Yes, please. Ooh, great question. Leverage, right? So it's a matter of leverage. Don't know how to explain that simply. I mean, you all know that concept, right? That if you want to open a door, you should push on the furthest side from the hinges, and it just opens much easier than if you push close to the hinges, right? Why is that? What's that? But you have a longer lever arm. So he's saying, why does a longer lever arm give you more twisting force? Yeah, Max, you want to give it a shot? Oh, you're asking a different question?
Yeah, so we're using the best product to use would be cross product because the cost is a crop, because we want maximum direction to use the bolt.
It's because when these are perpendicular, you get maximum torque. When they're parallel, how much torque do you get? You're just pulling on the wrench. It gives no torque. That's why it's cross product. So,
I can answer this question.
Oh, awesome, Kyle.
So, according to the BBC, the longer the lever, I looked it up. The longer the lever and the further the effort acts from the pivot, the greater the force on load will be. It is easier to use like a longer spanner when trying to turn a nut, and easier to push furthest from the hinges. So pretty much it's the farther you are away, the greater the force is multiplied.
Right. But you were asking why is that? You were asking why does a longer lever give you more force?
the farther you are away from your pivot, the greater the force.
But he's asking, what's the principle behind that? Why is it a longer lever? It gives you more. It feels natural, but how would you explain why?
Is there an R in the equation that gets squared or something like that? So if you increase R, you're getting a bigger number.
It's also why R's on the bottom of that. I'm pretty sure.
But the idea comes first, and then the equation fits the idea. So,
I
right?
was just trying to think of the idea. Why?
He's saying, why does a longer lever arm give you more torque? So how do you explain that? I have no idea how to explain that.
Yeah.
What's that? Twisting force.
Yeah.
Pretty much how much force will take.
Yes, R cross F.
Think of like.
So yes, it's the magnitude of R times the magnitude of F sine theta.
Yeah. Like,
Okay.
I was gonna hit card off my laptop.
Let's move on. Here we go.
Like that'd be $300
Any more questions about torque? Any more questions about torque? Okay, moving on. So here's another one, area. So when you have two vectors tail to tail, would you agree that they make a unique parallelogram? Would you agree with that? So if I got two, there's a unique parallelogram for those two vectors tail to tail. There's a unique parallelogram. Can you imagine it in your mind's eye, what that parallelogram is? So you'd repeat both those vectors and it would make a parallelogram. Okay, so what about, not that, not that. What's happening?
Technology's great.
All right, here we go. Ready? Now what about the area of the parallelogram? The area of the parallelogram, would it be a matter of dot product or cross product?
Area just a number, doesn't necessarily show direction.
Right, we're just talking about the magnitude. Is it the dot product or the magnitude of the cross product, right? So dot product or magnitude of the cross product area.
Magnitude of dot of the cross product.
Oh, it's on, right?
It's not product. Area is just a
Fight,
number.
fight.
If I take the area of
So-
the square, it's just going to show. It's just going to tell me. It's just going to give me a number. It's not going to show me the area is going in south direction.
Well, it's the same question we asked for the torque, right? I was just asking. My initial question was, is torque a matter of dot or cross product? And then we're just talking about magnitude of the cross product.
Yeah, so there's no direction.
Don't worry about the fact that cross product is a vector. Just which is going to be to calculate area? Would it be the dot product or the magnitude of the cross product? David, what do you think? Right, exactly. Here we said. So how much area do you get when they're in the same direction? 0. How much area do you get when they're orthogonal? Max. That would be cross or dot? Cross product. So let's see how this works. So what is the area of a parallelogram? Do you remember? So if I call this vector A and this vector B. So just back from geometry.
Length times width.
Okay, so the length times width. So like this side length times this side length? No.
Magnitude of each vector.
Height, right? It's about what? It's about the height. So I'll call the height h. So now if I had the height, what would the area be? Area would be h times, what about b? Magnitude b, right? You see that area of the base times the height is the parallelogram. It's not the side lengths multiplied. It's the area. It's the length of the base times the height. Okay. So what is h in terms of the vectors? The y component of a, or the So I'll give you a hint. Let's make that. So we got these tail to tail, right? So we got theta. So H is
Magnitude of A sine theta.
right. Magnitude of A, hypotenuse times sine theta. Can I put the sine theta at the end? Is that okay? And what do you notice? That is the magnitude of the cross product. So that what? What's the takeaway here? The magnitude of the cross product exactly gives the area of the unique parallelogram that you get when you put the vectors tail to tail. Now the actual cross product is a vector, and in what direction does that go? So what direction is A cross B?
Would be
What do you think? Oh, I thought you were erasing. You were trying to figure it out. Okay.
in the screen.
Some people, Cutter's saying into the screen. Into the screen. So we're going to point our index finger in A so that my third finger can point in the direction of B, and look at what my thumb does. If you said into the screen, you were right. Into the screen.
Okay, now
So this is called, so when we're talking about the area of that parallelogram and the direction perpendicular to the parallelogram, right? So that into the screen is perpendicular to the parallelogram. Then we refer to the A cross B as the area vector. It's called area vector. So it has the area of the parallelogram, and it's orthogonal to the parallelogram, according to the right-hand rule. So its magnitude is the area, and its direction is orthogonal to the parallelogram. Any questions on that? So don't answer, just think about it. Then do you also see that? Do you see that two vectors makes a unique triangle? Do you see that? So don't answer, think about it. How would you find the area of the triangle? So I think that's quite attainable. If you know the area of the parallelogram, the area of the triangle follows right from that. So this is the way you can use those vectors to find the area of the unique triangle that's formed by the two vectors. He suggested multiplying the area of the parallelogram by 1/2. Okay, I'll let you confirm it. All right, any questions on area or area vectors? Okay, so one more application here. This is kind of a cool one. It's called this is a three-dimensional object called a parallel pipet. So it's basically a prism. It's just a prism made out of parallelograms, right? Parallel pipet, prism made of parallelograms. And so what's the area? So now we're talking about volume. So volume is? So we'll be at just a general formula for volume here. What's that?
times width times height.
Okay, that would be if all the angles were right. So a little more general formula that would work here would be area of the base times height. So area of the base times height. Okay, we know what the area of the base is. What's the area of the base? Notice the magnitude of A cross B, right? We just saw that in the last parallelogram, right? So the area of the base is magnitude of A cross B. And then the height, notice what the height is. The height is what? It's the part of C in the direction orthogonal to A and B. Do you see that? So do you see that H is the part of C parallel to A cross B? So what do we want to do? We want to multiply as much of as much of C, as much as vector C, as is in the direction of A cross B. How do we do that? What would it be, Jake? Yeah. So dot product of what?
The cross product, right?
Cross product and
Or no, vector C.
right. So I want what? I want as much of C. The height is as much of C as is in the direction of A cross B. So this is the direction of A cross B, right? This is straight up because it's perpendicular. So I want as much of C as is in the direction of A cross B to get the height. What is that a matter of? I want to multiply the magnitude of the base times the magnitude of C, but only as much as is in this direction. But instead of using cosine, we can just write what? What is cosine? Dot product, right? Dot product. So we want the area of the base times the height. But what is the height? The height is as much as C as is in the direction of A cross B. So it's the dot product. Cross product of those two, get a vector, and do the dot product with C, and that'll give you the volume.
I got a question.
Sure.
Why can't you do
I love questions.
the magnitude of C sine, and if you found the angle of like C to the origin to A, you see what the angle I'm trying to make?
Yeah, so you could find angles and use angles, but the point is that with cross product and dot product, we don't have to know the angles.
Okay.
Do you see? That I can just do the cross product, that will give me the area of the base, and by doing the dot product, I get exactly as much of C as I need because it's the height.
Okay.
And I'm going to dot them together, so yeah, absolutely. You can find angles and just do it by geometry like you never knew vectors. But since we have these cross product and dot product that have like sine and cosine built right in, you can just use, don't have to ever calculate the angles.
That's the height, correct? Not the volume? Isn't the height the cross product A times B?
No, A cross B is the area of the base.
Uh-huh.
Right? That's the area of the base.
But the height's not C.
Right, but what does the dot product do? It multiplies the magnitudes only as much as they're in the same direction. That's what H is. See, H is the amount of C that's in the direction of A cross B.
I understand.
Does that make sense?
Yeah.
Super cool. Was there a hand in the back? Yeah, so this in effect gives us the area of the base times the height, because the dot C gives us only the part of C that we need, the height. Please.
Is this only for parallel parallel?
Yes. Or what else were you going to suggest?
No, like, because I'm thinking like for cube, but like, actually no, because it was a cube for the
It'll work for a cube. It'll work for a cube. It's just you wouldn't need, this is like overkill for a cube, because a cube you just cube the side length, right? But if you have a cube and you take the vectors of the cube and do this formula, it'll perfectly find the volume for you. Yeah, it'll work. Yes, please. That's the area of the parallelogram on the base. That's right. So just to review what dot product does, you get the area, or you get the magnitude of that times the magnitude of that, but only as much as they're in the same direction. Well, that's this direction, so that's how C turns into the height. Because it's only as much as A cross B, sorry, only as much as C is in the direction of A cross B, and that's how it gives you the height. Keep thinking about it. Just keep chewing on it. But this does exactly what we need it to do. It's gonna, yeah. So it's like the magnitude of A cross B times the magnitude of C, but what? Cosine of that phi angle, right? Does that help? So times cosine phi. But that's dot product, right? That's dot product. Go ahead. Nice enough. Okay. A cross B and C would be parallel. So you just get the product of the magnitudes for the dot product. Right? A cross B would be parallel to C if it were straight up. And then the dot product would give you the product of the magnitudes, which you want, right? Based on height. Good? Whew, we gotta move. Okay. So now we're gonna talk about lines. Lines in space. Okay, so to get a line in space, we're going to want to start with a point. So here I've got this point. It's the point 3, -3, 2. Just make sure that's right. Yep, 3, -3, 2. That's my point in space. And I want to define a line through that. What other thing what would be a convenient thing that would define a particular line through that point? What would be just one more mathematical or geometric entity that would define a particular line through that point? Direction. Okay. Well, what has direction? Vector, right? So, do you agree that if I had a vector, some vector, and I put its tail on that point, that it would define a unique line, right? Okay, so I'm going to start by taking that point 3, -3, 2. And I'm going to apply this vector. The blue vector is called the direction vector of the line. That's -1, 2, 1. And suddenly I just got another point on the line. What's the new point that I got on the line? Whose mouth is moving? Tell me. So,
2, -1, and 3.
Good. And how are you getting that?
By taking the initial and adding the stuff to get the line.
Right. So it's like, so I turn that point into a position vector, right? And so that point is the coordinates, but this vector also is 3, -3, 2. And if I add this vector, I get a new point in space. And is that point on the line? Absolutely. Okay, so that point is? So it's like 3, -3, 2, plus my direction vector, -1, 2, 1. And we got, for that, 2, -1, 3. And so we can write that, we can show that new point as a vector. So the black vector represents my like starting point or my like fixed point. And then my direction vector is parallel to the line. And then my red vector is can be any point on the line. So now how am I going to get more points on the line? What would I do to generate more points on this line? How would you generate another point? Chris?
Point on any part of the vector?
So what do I want to do? I want to do something to one of those vectors to get a new point. What should I do? Magnitude of? Yeah, scale. If I scale the direction vector, that would give me a new. So what if I scaled it by 2? So I just scaled the direction vector and made it by 2. And so that gives me a new point. Tell me what that point is now. It's a new point on the line. Still starting at 3, -3, 2. And I'm still using the same direction vector, -1, 2, 1, but what now? What about it? Multiplied by 2, right? And what new point do I get? One? 1, 0. Everyone see how we're getting that? So this is the idea of generating a line. You start at a fixed point, make that like a position vector, and then you take what? All scalar multiples of the direction. Is there a mistake?
Move the v vector before 0. Yeah, it should be.
This vector here?
Yeah.
Should be what now?
1,
The
1, 4.
1, 1, 4?
Yeah.
Thank you. We got it right now?
Yes.
Okay, cool. So how do we generate all points on the line then? What's the key to generating all points on the line? What's that? Of the direction vector, the blue one, right? So you do scalar multiplication. You take any scalar of the blue vector, you'll generate all points on the line. Even negative. So when you take negative scalars, that's going to point down and to the left, right? So any scalar will generate all points in that line, and the equation of the line is, so in general, what do we do? We started with a fixed point, and we're adding any scalar multiple of our direction vector. Sorry, that our initial point as a vector, plus all scalar multiples of the direction vector gives us all points on the line. So all points on the line, is that variable or fixed? Variable, so we're going to call that generically, that's our x, y, and z, right? So x, y, and z, this is like the red. This is the red vector, x, y, and z, all points on the line. Initial point, variable or fixed? We'll call that x naught, y naught, z naught. That was my, what is that in our problem? 3, -3, 2, right? Okay. And then? T, fixed or variable? Variable. V, fixed or variable? Fixed. So that would usually we call ABC. So how does the vector ABC relate to the line geometrically? Gives us direction, so we could say that it's what to the line? Parallel to the line, right? ABC is parallel to the line. X naught, Y naught, Z naught is a point on the line. So this is called the vector equation of a line.
Would you say the A, B, and C was?
That was this thing right here. So that's it's called the direction vector of the line, and it's pointing in the direction, and it's so you could say it's parallel. So I want you to find a point on this line that nobody else in the class is going to find. You figure out a point on this line that no one else in the class is going to do. Go. Every one of you, figure out the point on this line that nobody else in the class is going to figure out.
So like the X naught, Y naught.
There's an infinite number to choose from. Make sure yours is not the same as anybody else's in the class. How can you do that? Yeah, come on.
That's, so like the X naught, Y naught, whatever, that's the first initial one we have.
Right, so we're gonna add together the black vector plus a scalar multiple of the direction vector, the ABC, and the result is the red vector, pointing at every point of the line. So it's a vector addition problem, just like the picture. Who's dying to tell me their point that nobody else has? Philip, you got a good one?
I don't.
Not yet, okay? David, you got one? Say it again, say it nice and loud. -7, 17, 12. I think you're risking it there. I think there's possibility someone else could come. Is that a point on the line, first of all? So okay, now, how could you check see if that is a point on the line? So say I gave you this line. So actually, let's write out the equation of our line. What is the equation of our line? So now I want to apply this vector equation and write out the equation of our line. X, Y, Z equals, what does it equal? 3, -3, 2, plus? So now, someone came along and said, I think -7, 17, 12 is on the line. How can you verify that? How can you know for sure whether it's on the line? What can you do? What's that?
Plugging the point into the equation and solving for t.
Okay. So do that. So what t value corresponds to -7, 17, 12? So what you'll soon find out is, do you need all three?
No.
So the -7, where is that in this equation?
That's the x.
That would be the resulting x, right? So when x is -7, what does -7 equal? -7 equals 3 plus -t, right? 3 plus -1t, which means the t would have to be? Oh, David, that's a big risk right there. What kind of t should we pick so we make sure you don't get anyone else?
Infinity.
What's that?
E.
Oh, that sounds risky too.
Get that fractions.
I picked 87.
87 is getting better.
I got 25.
12.
0.0060.
How about 87.103 or something like that? Doesn't matter. So let's make sure that -7, 17, 12 is on the line. How do we know for sure that it is? How would we now check it? Use the x to figure out that t equals 10, and then what? Now plug 10 in t, and we should get 17 and 12, do we? Y equals? What does y equal? Negative 3 plus 2t. Do you see that? So, when t equals 10, $17, check. And z equals 2 plus t. T equals 10. 12. Check. That confirms. So we just confirmed that that point is definitely on the line. Okay, so what I did here, what these equations are right here, when you separate out equations into x, y, and z, so what I want you to do for the general form, so that was separating out x, y, I want you to do that for this general form. So separate out 3 equations, one for x, one for y, and one for z, from the general vector equation. Can you write those down? Try that. So write down 3 equations, one for x, one for y, one for z, from the vector equation. Let's see. Raj, can you do that? Tell me. X equals?
X equals to x naught plus 80.
Good.
Y equals to y naught plus bt. Z equals to z naught plus ct.
So, do you recognize those from Calc 2? When you have coordinates like x and y or x, y, and z, and they're all functions of a parameter t. So these are called the parametric equations of the line. Notice vectors are gone, right? When you write each coordinate individually, there's no more vectors anymore. And what we get is what's called a parametric function. T is the parameter, that's like the input. And then x, y, and z are the individual. So parametric function means a value of t gives you some coordinate triple x, y, z. It's the idea of a parametric function. Is it at least a little familiar from Calc 2? Should have had that in Calc 2.
Some teachers try to teach some things.
Well, so parametric function, yes, I understand that. But it is standard content for Calc 2. So that's why I'm kind of going slow and reviewing it.